Right, so that was a full step to find the derivative and find the tangent line. I find the tangent line, use the definition. Right? And then let's see another example. I find the derivative for f of x equals square root of x, use the definition. We have seen the difference of quotient of f of x to be radical x in our review, right? I hope you still remember, right? The f of x plus h minus f of x over h, right? Nothing to change that. This is our expression, and what we have seen, or even though from the last chapter, right, that this thing is called indeterminate when h goes to 0, that we have the difference n over h is simply undefined at h, right, which the difference of quotient should be defined everywhere in its domain. Right, at least should be defined everywhere for any h. Right, so what we can do in the review, we have also seen that multiply the conjugate pair to rationalize the numerator, that I get the difference of quotient which is h over h radical x plus h plus radical x. And that is this expression we have for the radical x. Then f prime of x is found by the prime in the way that the limit h goes to 0 of this expression. I could skip some steps, right? Reasonable. That when h approaches to 0, we get is 1 over x plus 0 plus radical x. That's 1 over radical x plus radical x. Right, when we approach h to 0 into the difference of quotient, we get that. And then what we get is 1 over 2 radical x as the result of f of x to be radical x. Right, that is what's the derivative. So that was the example we have seen, and try something. Negative 2 radical x, or let's say negative 2 radical x minus 1. Right, similarly, if we break down into steps, what we could do is f of x plus h, negative 2 radical x plus h minus 1, nothing happens. F of x plus h minus f of x, that's a negative 2 radical x plus h minus 1 minus negative 2 radical x minus 1. One benefit here is if we factor out the negative 2, it might be a little helpful. And when we factor out the quotient, it should be a little more helpful, since when we do the difference of quotient, we not count the coefficient in there. Right, that is the difference. Then we do the difference of quotient. Right, in this case, then we multiply its conjugate pair. Multiply radical x plus h minus 1 plus radical x minus 1. Right? Multiply the conjugate pair, then this product will still give us the difference of squares. Right, the difference of squares, which are the square of the radical, and the denominator we get radical x plus h minus 1 plus radical x minus 1. The top x plus h minus 1 minus x plus 1, that is left over the h. And that's what this thing left over. And then that thing equal negative 2 over radical x plus h minus 1 plus radical x minus 1. Right, for the h being cancelled out. Therefore, the f prime of x, taking limit for h approaches to 0 of this term, that's negative 2 over radical x minus 1 plus radical x minus 1. Right? Negative 2 over 2 radical x minus 1. That's negative 1 over square root of x minus 1. I simplify the algebraic expression. At the end, we get the derivative of negative 2 radical x minus 1 equals negative 1 over square root x minus 1. And that's what we have found for radical expression. Another way, or another thing to be very classic, f of x equals 1 over x, use the definition. Right, so we have seen that, right? F of x plus h equals 1 over x plus h, f of x plus h minus f of x, that is 1 over x plus h minus 1 over x. What we had seen before is this thing could be simplified to one fraction. If I multiply the first equation by x, second expression by x plus h, top and bottom, I will get x over x plus h times x minus x plus h over x times x plus h. Right, to one expression and simplify. Right, that we have x minus h, we have is negative h over x times x plus h. Right, hope you can understand, right? Just expand that out and x will be cancelled out. We have negative h left over. Then the quotient, negative h x plus h over h, that we can, since it's a fraction, we can flip it and multiply. Or flip the denominator to be 1 over h, then it's become h to be cancelled out. That's negative 1 over x times x plus h. Right, then finally, for f prime of x, that's the limit as h goes to 0 for the expression negative 1 over x plus h. That's negative 1 over x times x plus 0, which is negative 1 over x squared. Right. For a fraction, we have the way, right? We summarized before. We have the way to make them to be single fraction and simplify. Then afterwards, we can multiply 1 over h to get the quotient and simplify. Then the extra step to find the derivative is just to make h goes to 0. Right, take the limit of this expression. For the variable here, just h as the variable. X is x, basically. Right? X is not the variable, only h is the limit we take, right? The approximate to. H is the variable of this limit. When it goes to 0, we get the expression of f prime of x as the function negative 1 over x squared. Right, so wrapping up, try an example. Try to do that. Find f prime of x for f of x equals x minus 4 of x. Use the definition. Right, so in this section, when we see use the definition, we means use the limit definition. Right? If you don't see this word, what we have a simplified formula in the next section, right? But in our section 3.1, we are following the limit definition. So when we see use definition, we have to use it. So first, f of x plus h, that is x plus h minus 4 over x plus h. Nothing special. Then find the difference. that is x plus h minus 4 of x plus h minus x minus 4 of x. I give parentheses. What we have is the x being cancelled. We have the term of h. Negative 4 of x plus h plus 4 over x, which is kind of a little separated, right? The h is perfectly stays as the h. And the two fractions here, we need to make them together. It's like the polynomial is a rational expression, two different ways to do this question. Right? Two different approaches. When you combine the fractions, you could use the positive sign. What we can do is, that is a minus, which is simply a plus a negative sign. Right, so we could make it a positive and just ask the numerator to be negative. Right, that is one small technique. Negative 4x plus 4x plus 4h. And that is, we have h plus 4h over x times x plus h. Right, that's the difference. And then the quotient f of x plus h minus f of x over h, that's h, 4h over. What you can also do is factor the h out on the numerator. That's 1 plus 4 over x times x plus h. And in that case, you could factor or divide the h, right, plus. And that's the difference of quotient. And then when we take the derivative f prime of x, we just take the limit as h equals to 0. Limit at h equals to 0 of this expression that we have is 1 plus four over x times x plus 0, that is x squared. Well, we have 1 plus 4 over x squared. Right, so that's something somehow wraps up the polynomial with the rational expression. And maybe you will see more practice in your homework. But that is what we have. Another expression for the derivative, right? We have and arbitrary point x, we have a fixed point c, right? So the x f of x, c f of c is the function. Then the slope of secant line is f of x minus f of c over x minus c. So if we want to find the tangent line slope at this given point c, what we can let is let the x value approaches to that c value along the path, right? Or along here, or along the path, right? Both of them. Then we yield the x approaches to c as the alternative definition at the derivative at c. And the definition is talking about the differentiability. F of x is differentiable at x equals c if the limit as x approaches tc from the left of the difference of quotient equals the limit which means your c could be arbitrarily from the left side and approach to that. And when you approach the difference of quotient from the left and from the right, they are yield a same value. That we can see the derivative exists. But basically, we can see f of c need to be defined. F of c defined. And maybe we are able to find what the left and the right derivative are not same. That means it's undifferentiable, right? But if it is differentiable, then if the limit exists from the left and from the right are equal, then it is differentiable at x equals c. In other words, they need to be exist and equal. Then we say function is differentiable. And in some case, the limits not exist. In some case, they are exist, both of them exist, but not equal. Then we say function is not differentiable. For them. If the limit exists and equal, then exist. Okay, so use the definition. To show something. To show that, well, f of x equal absolute of x minus 2 is not differentiable at x equal 2. And we got that's the expression, right? What we have, the x minus 2 is the straight line that it is from the right is it's increasing to infinity at the left, but before 2 is negative. When we flip it, when we have the absolute value, it will be flipped top, right? Originally, that is what the x minus 2 is, right? But the absolute function will flip mirroring with that and flip the line up to get this picture. Right, so for something, right, f of x equals, for piecewise, x minus 2 for x is 0 positive, negative of x minus 2 for x is less than 2. Right, that is how the absolute value function defined. Right, for the inside to be positive, it is the inside. For the inside to be negative, that will be negative of whatever inside. Right, so what we need to show is, well, maybe the left or the right doesn't exist, or if they exist, they are not equal. Right, so we need to show the x approaches 2 from the left. Maybe exist, maybe not. Right. So for x approaches to 2 from the left, that means x is smaller than 2. And this thing means x is smaller than 2. Therefore, the function here, we use the second piece. And f of 2 for the piecewise function, I have the wrong formula before. Now it's correct. Right? The difference of y over the difference of x. The f of 2 anyway is a 0. Negative x minus 2 over x minus 2. As we can see, right, the slope of this line is negative 1, which is the f prime of 2 when x approaches to 2 from the left side is negative 1. But also on the other side we have a slope of positive 1, then their derivatives are not equal, right? But let's see. From 2 from the right side, from the right side means x is positive. That's x minus 2 minus 0 of x minus 2. Equal 1. Right, so the right side we get derivative approximated to be, the derivative is to be 1. The left side derivative is to be negative 1. And therefore, the limit to from the left have to write it, not equal to limit from the right. That's what we see, right? From the left it's negative 1, from the right is 1. Therefore they are not equal. So f of x is not differentiable. At this point. right? Not differentiable at x equal 2, but elsewhere is differentiable, right? Everything up to 2, or everything after 2, everything before 2, right? And everything after 2 are differentiable, but only not differentiable at this 2. That is the case that, well, we have absolute function, it is not differentiable. Since, well, from the conclusion we see the left side, right side derivative are not same. And graphically, right, we can see that, well, the graph is continuous, but it's not that much smoothly continuous. It is a sudden change of the pattern, right? From the left, it's just simply going down, but suddenly, right, change to up. When you move along the path of the curve, it has a sudden change. That means it is not differentiable. Right, what it can see is not equal. Right? Both of them exist, but that is sudden change that makes it not equal at this point. Makes not differentiable. X to the 1/3 is a cubic radical, cube root of x, which every odd radical of x, of any variable, is defined everywhere, right, for odd radicals. Here we have cube root of x, which is defined everywhere, defined at 0. The 0 to the 1/3 is cube root of 0, which is a 0, but to show that it is not differentiable at x equals 0. It looks like it's smoothly continuous, right? Nothing sudden change at the 0, but let's see what happens actually. The limit from the left of f of x minus f of 0 over x minus 0 f of x is x to the 3rd, f of 0 is 0 to the 1/3, and that is x, right? So when we simplify it, that's limit x approaches to the 0 from the left of x to the 3rd over x. Right? If you remember that for the rational expression, division of same power, of different power, same base, that's equal to the difference of the power, or that's equal 1 over the denominator, if we keep it, 1 over n over minus n. Right, that's x to the 1/3 over x. That will become x to the negative 2/3, or simply that's 1 over x to the 2/3. If we simplify that to back into radical, that's cube root of x squared. Which approach to 0, this one doesn't exist as not defined, but for its approaching value we get 1 over cube root a little less than 0 but squared. When we square the negative 0, we'll get a positive number. And when we take cube root of a 0, that's a 0. Right, that is infinity, which means does not exist. Right, the limit is infinity, it means it's unbounded. The direction goes to positive infinity, which simply just means this thing doesn't exist. Right, once we find the limit to be infinity, we can say f of x is not differentiable. Or we can simply say f of x is not differentiable at x equals 0. Why? Because it's not exist. What we had the definition saying, well, it's differentiable at x equals c if the derivative from the left and from the right need to be exist and are equal. Right? First of all, this limit from the left side doesn't exist, then yields to not differentiable. Now, even though it looks like smoothly continuous, but here we have a derivative to be infinity, right? Which means derivative is not exist. We have an infinity, a negative infinity. Maybe you have seen that thing before as the vertical line, right? Has the slope of infinity. So we have a vertical tangent line here, which means not exist. Which means the derivative not exist. And also that means it's not differentiable. Not differentiable. Another short, easy example is show that the piecewise function is not differentiable at x equals 1. Right, for the piecewise function, if we graph it, right, still, for x to be after 1, that is a 1 here. For x to be less than or equal 1, and that's a point here. So it simply breaks, right? From the graph, we already see it should be not differentiable since it's not continuous, right? But we didn't talk about the relationship between continuity and differentiability yet. But as we see, f of c has to be defined at least. In this case, f of c is defined. Right, but later we'll see that f of c need to be continuous, but let's see. The limit, well, basically f of 1 is equal 2 times 1 minus 3 is negative 1. Right, so the limit of f of x approach to 1 from the left where x is smaller than 1, that we have the function of 2x minus 3. that we have is 2x minus 2 or x minus 1. We're able to factor out the 2 and divide it, that's 2. Then we get the limit when x approaches to the left is 2. Well, but let's check the right side. For x bigger than 1, that is x squared minus negative 1 over x minus 1. That is a little bit bigger and a little bit bigger. It doesn't exist. And from the right, it does not exist in that way. Therefore, we have a side that doesn't exist. We have left side that exists. But on this case, in this case, we can officially say f of x is not differentiable at x equals 1. Last important thing, if f is differentiable, continuous. But not vice versa. Right? If f is differentiable, then f is continuous. But not vice versa means if f is continuous, we cannot say f is differentiable. We can only say is if f is not continuous, then f is not differentiable. Right? That's something about the logic. So let's see the proof. Right, the limit of the difference equals, if we can attach a denominator, and when we take it out, since x minus c is a constant, it's not a constant, that's a different limit. If this expression exists that is f prime of c, then this expression is a 0, that means it's a 0. Right? So that over here shows the differentiability. Then what we have is limit of x approaches c of f of x equals to defined f of c, which the limit exists and equal to function value, which is the condition of function is continuous at f of c. So if the limit exists, then function has to be continuous. right? But for function to be continuous, we cannot say it's differentiable. Right? Like the thing is absolute, like the thing is of cubic radical. They both are continuous function, but not differentiable at a certain point. Right, so that is everything of section 3.1, and we'll move on to the next part. Right, the limit definition is kind of a little tricky, right? A lot of steps to do, but later on we have some simpler version of formula to see, which will be a little bit easier.